Hi guys. Law of universal gravitation. I want to go through this. This is one of those things that's really a high point of human achievement. So it's a really big deal. We've seen gravity before, but we've talked about it in terms of weight. We'd say it was equal to minus mg, where g was 9.81 meters per second squared on the Earth. And then in some sapling questions, we've talked about it being a different number on other planets. Where does that number come from? That's what we want to discuss. So today we're going to go through Newton's law of universal gravitation, which explains the true nature of gravity, at least until you need to know about Einstein and general relativity. So with this law, we will use it to explain where 9.81 actually comes from, and we will also use it to describe and determine the mass of the sun and also the mass of the Earth. And then if you get the idea of those, you can pretty much get a flavor of how we determine masses of things out in space. Very good. So to start out, you need to step into your of Newton. And so at the time of Newton, it was known because of Kepler that planets traveled on elliptical orbits where the sun was placed at one of the focal points. Furthermore, it was known, basically just via numerology and trial and error and fitting data, that the period squared of the planetary orbits was proportional to actually the semi-major axis of the elliptical orbit. In terms of a circle, the semi-major axis would just be the radius. Okay, so because a circle is a special case of an ellipse. And on top of that, it was known via Galileo that when you drop things near the Earth's surface, wait for it, wait for it, wait for it. I apologize, I don't have my correct equipment, but if you drop things near the Earth's surface, whether they are large or small, if you do it today, tomorrow, or the next day, or apparently in front of a webcam and on the internet, when you measure the acceleration due to gravity, it's always Newton came along. These things were known, at least to some people. And so Newton had developed his concepts of motion, his laws of motion. And he was then, he then wanted to use those to explain where Kepler's laws came from, specifically the elliptical orbits and the period squared being related to the semi-major axis cubed of the orbits. So the mental picture that Newton started with might surprise you. You see, his starting point, in his day, he didn't start out knowing that gravity had anything to do with the planets. So for him, gravity was the thing which makes stuff fall. And he knew that gravity made all things fall at the same rate. It was a completely different phenomenon that planets orbited the sun and moons orbit the planets, et cetera, et cetera. So to kind of link these concepts, Newton imagined the following picture. Remember, he lived in a time after as a person of that time, So imagine you had a cannon. So, oh, in case you couldn't tell, or for those of you who still think the Earth is flat, this is the Earth. It's round. And I went ahead and put a mountain on top of the Earth. And I'm going to imagine that you shoot a cannonball off the side of this mountain. Now, at first, let's imagine that you just put a little bit of gunpowder in. Doesn't go very far. I hope you can see that even. I'll make the dots bigger. It's not very impressive. So instead, let's imagine that we added extra gunpowder. And it would go a little bit farther. Notice, the cannonball is falling, and everybody would have said that it was falling because of Earth's gravity. It was pulled towards the surface of the Earth. No mystery there. But let's imagine you keep adding more and more gunpowder. So you keep adding more gunpowder. And notice the cannonball is still falling. It's always falling. It's always falling. But look what happens. As it falls, the cannonball would hit the Earth at some moment at this point. But because the Earth is round and spherical, by the time the cannonball has fallen this much, the Earth is kind of cut away. So there's no ground there to hit. And so the cannonball keeps on falling and falling and ends up landing over here. Finally, you get the idea that if you added enough gunpowder and if you didn't have wind resistance and all that, you basically could send something around and it would return to where it started. So if you're not careful, you could shoot yourself in the back of the head or something. And at which point, the cannonball has gone around once, and if there's no wind resistance, no friction, it goes around once, gets back to where it started with the same speed. So it goes around again and again and again. And this is how Newton realized that he could connect the concepts of gravity on the Earth, namely the reason things fall, with orbits of planets and objects in the heavens. And I think before that, it wasn't clear that these concepts had anything to do with each other. Okay, so this is the mental picture you should have for what is gravity. And notice then, it also lets you realize that when we have astronauts in a satellite in the space station floating around the Earth, going around the Earth, that's not really true because they're orbiting the Earth. What keeps them in orbit? Earth's gravitational force. That means they have a weight. What they don't have is a normal force pressing on their body. And so they don't perceive the weight because they can't feel it. They're just floating. And what happens is they fall towards the Earth's surface, but when they get wherever they're going, the Earth is moved out of the way because the Earth is round. So there's no place for them to hit, and they just keep going around and around and around. Okay, so that's kind of one observation. Great. Next up, I want to go through Newton's formula that he deduced for the form of the universal law of gravitation. I say it's universal, and that really goes back to Galileo noticing that all things fall at the same acceleration. Well, it's going to turn out that Newton's law of universal gravitation applies to any two objects. So if you guys are in class, I would say, Josh and Mason in the back are being attracted to each other via Newton's law of gravitation, just because all things feel this force. Down the formula that he deduced. So if there were two objects, I could have planet 1 and planet 2. Okay, planet 1 and planet 2. And I can go ahead and label the vector or the distance between them. So I'm going to call this R from 1 to 2, R1, 2. It just is the relative vector, not some vector relative compared to some other reference frame. It's the vector straight line between the two. And what Newton concluded is that there's a force which acts on these objects, and he deduced, well, so how did he deduce this? Step 1, be Isaac Newton. Step 2, write the answer down. I don't know. To be honest, I don't know how he figured it out. I presume he tried many different functions until he got something that was compatible with Kepler's laws. I don't know. Anyway, his proposal was that the force of gravity between two objects, so between 1 and 2, this constant G. I'm not sure what symbol Newton used. He may have just said proportional. G times the mass of the first object, or planet or star, whatever, times the mass of the second planet or star, and it's divided by the distance between them squared. Now, this is actually the formula for the magnitude of the force of gravity. The actual force, then, to make it a vector, you need to specify the direction, and for each object, it draws them together. So if you're standing at 2, the force would act towards 1, drawing it towards object 1. If you're at object 1, the force of gravity would pull it towards object 2, so it would be to the right. Okay, so, okay. This is the first example that you guys have seen, at least with me, of something called an inverse square law. Inverse square laws are very important in nature. They come up whenever you have a quantity that spreads out somehow through all of space and are associated with a conserved quantity, conserved amount. In this case, it's connected to the exactly correct. And so you shouldn't be surprised that this formula is not exactly correct. If you can improve upon it using relativity, but this works very well. Other conservation laws are things like charge conservation. And indeed, if you study electrical forces between 2 point charges, you find essentially the same force law, where instead of masses, you have charge. You have a different constant here, but otherwise it's the same for the same reason. Anytime you have a classical theory of conserved charges, you expect something like this. Okay, I said point charges. I also should have said, really, I'm talking about point masses. And if we want to apply this to an entire planet, what we need to do, well, if you want to take into account the true variation of forces as you move through the core of the planet, around the core of the Earth, you need calculus 3 technology. You have to learn about something called Gauss's law. In this case, though, we will only be talking about forces on maybe planets that are widely separated. And so we really just want to imagine these points represent the centers of the planets. So okay. This is Newton's law of universal gravitation. It applies to all objects regardless of where they are in space. And you can do a quick estimate. So let's imagine, we can't do any estimates because we don't know the number. So in Newton's day, he did not know experimentally what this number needed to be. And we now call it, I'm not sure what what we called it. We now call it G is the Newton's gravitational constant. L constant. Or sometimes it's called the constant of universal gravitation, or some variation thereof. Okay? Outstanding. The way it was determined is as follows. Some of you guys probably noticed I have this, oh dear, I'll just bend this down. You've seen this in the classroom, I'm sure, and wondered what is going on. Why does Sean have cannonballs? What this is what's an experiment. The original named Cavendish, and it turns out, if you take two cannonballs, Newton would say there is some gravitational force between them, but we just know it's exceedingly small from our everyday life. And so one of the challenges in this case is to measure a number which is going to have to be a tiny number. It turns out G is just almost an inconceivably small number. So the way Cavendish proposed to do this was to, first he had a rope hanging from a tall place, I assume a tall building. And what he did was he had cannonballs, and he could arrange them at different positions like this. So it's on a swivel, it twists. And what he had, I'll take this off for a second. He had a horizontal bar with some masses hanging, suspended on the bar. And now this actual piece has been broken. There's a wire that's snapped in it. But what would happen is there are little balls suspended here, and they would be free to twist. So the idea is that if you put cannonballs near these small suspended masses, it will cause the arm of the so that you could shine a laser or something off of a mirror that was in this little window, and if it would bounce off, and as the arm here would twist, you could measure the deflection, which is caused by the gravitational forces acting on the suspended masses. And if the wire was very precisely calibrated, you could use this like a torsion balance in essence, and measure the force of gravity acting on these objects. So this is an experiment by a man named Cavendish. It would be nice to have one at the college, a large one, a big one. One of the challenges is it's very touchy, and given that we have air conditioning units on the ceiling that make the ceiling pulse, I don't think we would be able to get good results, at least not in the physics room. Okay, so the output of Cavendish's experiment is that G is the following number: 6.67 times 10 to the negative 11. It's tiny. Let's think about units. I need to get newtons here. We have meters here. We have kilogram times kilogram here. So G has to have units of Newton meters squared per kilogram squared. It's a tiny number, and that reflects the very weak gravitational forces for things of everyday size. You really need something the size of a planet or star to make this a significant force. Let's work out an example. I don't know if you remember the radius of the Earth. It is about the width. So I think that's about 4,000 miles. We can use Newton's law of universal gravitation to explain lots of things that we've seen already. For example, we can use it to explain where 9.81 comes from. And I'm going to just use 6,000 as an approximate radius of the Earth. If you put in the real number, you'll get a better estimate. Okay, so let's imagine that you're on Earth, and we are going to assume that the radius of the Earth is 6,000 kilometers, or 6 times 10 to the 6 meters. In fact, we can do better. Using the intertubes, radius of the Earth, 6,000, let's call it 6.4. 6.4 thousand or million meters. Okay, very good. And while we're at it, so what we want to do is use this to understand where 9.81 comes from. So to do this, we're going to apply Newton's law of universal gravitation to a person standing on the Earth. And so to do that, we've got two objects. So I'm going to get rid of this picture. And just imagine I have two objects. And what is the distance between their centers? Well, pretty much the distance between you and the center of the Earth is just the radius of the Earth. The extra, whatever, 2 meters doesn't matter. So the distance between the two objects is simply the radius of the Earth. And the force, net force on, or I guess the gravitational force on something is equal to G times the mass of the Earth times the mass of the object or person. So it could be you, it could be a person, doesn't matter. Divided by the radius of the Earth squared. So if we run the numbers, what we find is that G, which is 6.67 times 10 to the negative 11, times the mass of the Earth. Well, you may not know this number, but the mass of the Earth, I believe is like 5.2 times 10 to the 24. It's a big one, 24 kilograms. And then we need to divide by the radius of the Earth squared. So the radius of the Earth is 6.4 times 10 to the 6th squared. So if I type all this in, I'll use the phone here. I'm going to have 6.67 times 10 raised to the negative 11 times 5.2 times 10 raised to the 24 divided by the quantity 6.4 times 10 raised to the 6th quantity. Oh, go back one. And then squared. I think I've typed it all in right. Oh, I apologize. I'm going to cheat here and get the mass of the Earth. Very good. 5.9. Sometimes my memory just doesn't work. Let's try that again. I apologize. Okay, so this number gives me approximately 9.6. If you put in the right numbers and you get all the digits, you'll get the right answer, 9.81. So this is where where G comes out. In fact, let me put in a more accurate value for the mass of the Earth. Yeah. So if you add in more and more accurate numbers, I rounded things a bit too much here. Okay. So as I add in more numbers, I'm getting 9.81 or 8. It's just a matter of getting the right numbers. So 9.81. And I apologize. I should have finished here. I multiplied G, M, and R stuff. I still have the mass of the person or object. So we now know the real numbers when you plug them all in is that the force of gravity, or otherwise known as weight, is 9.81 times the mass of the person or thing. So in fact, that means that this is G, which means that what we've been calling G is actually connected to Newton's universal gravitational constant times the mass of the Earth divided by the radius of the Earth squared. So that's an interesting fact. That explains where the 9.81 number comes from.